Log on, tune in, find out. Another good idea from Cambridge.
Speaking about this very topic.
Okay. Thank you very much. Probably you realize that it's a little bit different title than I advertised, and actually Bill made it a little bit on short notice, or I was late, whatever the reason. And it was called Sectional Imaging for Photoacoustic Imaging. So imaging is an important topic, but probably not that as it's in the original title. So let me first give a short overview on what is photoacoustic imaging doing, and I guess the best explanation is of Li-Hong Wang, who described it as lightning and thunder. So what you usually do is you expose a probe or a specimen by a short pulse, electromagnetic pulse, and then when this happens, you produce sound waves which are propagating through the specimen, and you record the sound waves, and then you reconstruct from the induced sound waves material properties. So actually it's now a quite complicated thing which is going on there, so because the probe absorbs the electromagnetic energy. Well, naive thinking, which is probably not right, but the body heats up, and then the material reacts with a local expansion, which is different for at different materials. So what we then are actually doing is we just record not we, but what one does is one records the pressure waves, and from these one does some mathematics to reconstruct the material properties. And there are different names, so photoacoustic is also sometimes called thermoacoustics. So I think one differentiation would be that if you illuminate with infrared light, then you call it photoacoustics. With microwaves, probably you call it thermoacoustics. So there have been a lot of applications discussed for this. So there's very early publications and patents by Kruger, which are already in the 1995. And he built a breast scanner for tumor screening, and I guess they evaluated 1,000 patients or whatever. Now there's also a European counterpart, which is done by Manohar, who has this Twente photoacoustic mammoscope project, where they do very similar things in clinical applications. Brain imaging, probably not of human, but of rats, have been done by Li-Hong Wang and Paul Beard. There's also another project which is probably more relevant for this audience, which is project of Adonis. And so this is mainly, I mean, the mathematical or the physical part is done by Martin Frenz. And then there's also the gene research, which actually comes more close to what we are doing, which is the group of Rasansky, for instance, in Munich. So it's more microscopic applications and much smaller size. So here are some experimental setups, just to show you how it actually works. The left one is from Martin Frenz groups, from Joel Niederhauser, and he uses this as a combined, he had already, I think 7 or 8 years ago, a combined, or 10 years ago probably, a combined ultrasound and photoacoustic detector. So what they do is they send in addition to the classical pulses of this ultrasound, they send also a laser light, which it's red light. And then they reconstruct both the ultrasound waves with classical techniques and also some photoacoustic inversion techniques. Well, we call it microscopic, which is in the clinical applications probably not the correct thing to do. Well, they also call it tomographic sometimes. But we call it microscopic because the probe doesn't have to be moved. It's just or not rotated around the object. Just a scanner. You just scan. So this is one of the setups which we have done. So we shine a laser onto the specimen, and you see at the top you have to rotate the specimen to get enough data. And when we're doing this rotation, we call it tomographic. So we have to collect pressure data by moving the object, or the tank, whatever you want, what's more convenient for you, and to get enough reconstruction data for the 3D imaging. So the mathematics of this model, and well, this is still the standard model, is very simple. So what you actually just model is the wave propagation. So we have a 2D or 3D wave equation model. Usually, as it's written down here, it's 3D, but sometimes you can also derive 2D models. And then you have something which is represented by this J here, which is the illumination of the laser. And here you have what's actually interesting. This is the material properties. And as you see here, the material properties are actually a combination of several parameters. I mean, you can describe it in different combinations as well. But for instance, here you have a heat capacity, which somehow tells you how much is transferred of the energy into sound waves, absorption, thermal expansion coefficients, and some other things. So these are material properties, and this is the laser characteristics. And in the simplest case, one usually takes that the laser impulse is very short, so nanoseconds, and then we approximate it by delta impulse. This makes life a little bit simpler, but not that much. So this is really that we use a pulsed energy and we model it by a delta impulse then. And if you do this, model it by delta impulse, you can rewrite this inhomogeneous equation in a standard form, where you have just a homogeneous equation and you have initial data and initial data for the pressure and for the time distribution. So then this term cancels, and so you have just this initial data here. So the material properties then just show up as the initial data of the wave equation. And this is what you want to reconstruct by some measurements. So to summarize, the imaging problem is then very simple. If you look on tomographic applications, and I will mainly concentrate on the tomographic applications, you take a surface which surrounds the specimen or the probe. You measure over the time, let's say infinite time, for simplicity, the pressure. At some detectors or whatever, I will show you some measurement devices later on. And then you reconstruct from this the spatial variable function f. But all what you do is you don't get out one of these physical parameters, but you get out a real combination of 4 to 5 whatever parameters. So, okay, so now we have the model, and now we have to somehow explain what we are really measuring. So the earliest and I think most common approach is that they use small piezo crystals, which are positioned around the specimen, which you also have seen in these ultrasound detectors, because they're just, each piezo crystal just detects a signal, and so these crystals record the pressure field, and then you do the reconstruction. And in mathematical terms, it's just an inversion of the wave equation, or backpropagating of the wave equation, which you can write down in back projection formulas, for instance, if you have enough data, and actually you can reduce it to the reconstruction over spherical means. So what you actually mathematically have is you collect pressure data, which are averages over the pressure over spheres, and then you do some use some back projection formulas from these average data. So what we have done, and I show you just that as motivation. Originally, we have started to work with big detectors, so just in the opposite direction of here. Here, the small piezo crystals are considered as points in the mathematical formulations. And here we considered, relatively large detectors. For instance, here the whole detector detects an average pressure field. So this is, for instance, where you measure the averaged area over a large plane. And then if you do it optically, which is, I guess, represented here, then you can actually measure the averaged pressure over lines. So in addition that we have the propagation of the sound waves, which produces somehow averages over sphere, we then do an additional convolution to model these equations over planes or over lines. So another comment, I will do this on the probably last few slides. Photoacoustic is a very rough model. I think just only recently, recently is relative, but there have been some things some research to take into account more modeling aspects. One of them, for instance, is that sound speed variations have not been considered up to a few years ago in photoacoustics. That's probably related to the probes which have been investigated. But there are some, I think, severe mathematical arguments that one should do it and how one should do it. Also, what is not considered is typically attenuation of the sound waves. So that the waves are, for instance, frequency dependent, attenuated over travel time. There are several models, but I think no real model has been established, which is really the one which should be used in photoacoustics. Also, what has not been taken into account, and this relates to what not has been taken into account very seriously, is the illumination. You can do it in the terms of qualitative photoacoustics. Quantitative, it should mean quantitative. I always mix them up, so it's quantitative. Sorry. In terms of how much illumination you actually get into the probe and at which locations. So I guess there's, in every of these 4 points, one should mention Li Hong Wang has definitely worked on other projects, but this, I guess, is really what he did also experimentally. So I'm going back to this illumination, and this is now the thing where I come to this sliced photoacoustics. So I really want to do now steer the illumination to get some more reasonable some other information than the classical photoacoustic stuff. So these are now the probes which we are considering. This is our zebrafish model. It's not something big, but it's a few millimeters. So in diameter, it's about 1 to 2 millimeters, which is the thickness of the fish. And sectional imaging or sliced imaging means that we concentrate with the illumination to a certain region, to a certain plane of the fish. So what's actually done is they use some lenses to focus the light to a certain region of the fish, and the illumination has to happen relatively far away from the fish, which is a drawback of this method, that you get a focal zone which is really in the center of the fish. So one can imagine that the laser is, let's say, here, and inside here it's very narrow, where it's illuminated, but outside of, obviously, you take some contact material which doesn't give you perturbations of the sound waves, but inside here you get the real information. There are several advantages why you can do it. If you do the standard photoacoustic problem, you have to use a uniform illumination, so you have to use a very high energy to illuminate the whole object, which sometimes hurt. Well, the fish is dead anyhow, but it hurts the fish. So if you do it slice by slice, you can work with much less energy to record each slice. And there are the realizations is usually done with illuminations, like in ultrasound transducers, but here they do it with electromagnetic waves, which are focused to this region. But essentially, the idea is just to bring the energy to some focal point in the center. So there are some disadvantages with these methods. You have to take into account some blurring experiments. But nevertheless, you see that for these fish, exactly for these slices which are written here, well, the resolution is low, but this is the fish which is recorded then slice by slice, so each slice is recorded. And it's unfortunately not done, or now we know the reason why this works, but it's a method which our physics colleagues have invented, which is not mathematically exact, but still works very well. The reason is that there is some additional transformation required, which is not that relevant in the focal zone. But anyway, so this is the step by step through the fish. And here, for instance, you see the fins popping up. It's not a flea, but it's really a fish, slice by slice. So now we come to a very rough model. It's not the ultimate thing, I guess, which we want to do. We want to do eventually a more accurate modeling of the lenses. But if you think of just of the illumination in the focal zone, it's probably a reasonable model to start with. So what we do is we model the illumination at a certain depth with this delta distribution. So this means we just concentrate on one plane. So Z would be the depth direction. And then we only want to reconstruct a two-dimensional function. We do it slice by slice, so eventually we can also build up a three-dimensional imaging. And now the problem of photoacoustics we have formulated as an initial condition is, so you have the wave equation. I write here down other coordinates just to visualize this. This is the two-dimensional plane, and this is the depth direction. And then you assume some initial conditions, which are now delta distribution in depth direction, plus the two-dimensional image which you want to reconstruct. Nevertheless, the problem is the wave equation is still three-dimensional, so it's you can record the data also in different positions. So you don't have to record them into the plane, but you can record them also in other positions. So, and the reconstruction problem is then a two-dimensional problem, also the equation is three-dimensional. So we want to recover this function f tilde from measurements outside of the specimen. So now there comes a little technical slide. The reason why I'm doing this is I want to work with arbitrary geometry, which then I want to do a reconstruction. So I want to record the data on an arbitrary domain which surrounds the probe. You don't have to do to consider this slice if you just work on planes or on lines which are around the object, or on circles, then this is just, well, then you have just polar coordinates. But if you do it arbitrarily, then it's very convenient to, well, first of all, I have to say I have to restrict myself to convex domains, and I have to parameterize the boundary of the convex domain. And I do it in a, well, probably a little unnatural way. So I take the angle, and from the angle I construct the tangent point of the, let's say for instance, of the ellipsis. So for each angle I get the tangent point. And with this parameterization, angle to tangent point, I will do the reconstructions. So it's not very detailed, but it's just a parameterization of the, with respect to the tangent points of the object which surrounds the probe. And with this I can handle, I can get back projection formula or series expansions for essentially for arbitrary domains which surround the probe relatively easily. So now I'm looking for this sliced imaging, and there are several ways how you can do it with these detectors. So one of them is you use point detectors, and then you usually position them in the plane where you record the where you want to reconstruct. So you put them really on the same, in the same plane where you reconstruct. Then you can do it with, I always mix up vertical and horizontal as well. So you can put in vertical, yeah, horizontal, vertical lines, line detectors. So this means you illuminate in this direction and you measure along lines in this direction, which is, I think, a very good approach to do this. You can do it with large planes. So illuminate in this direction, measure the averaged pressure over this line. And then you can do it also, if you do it like here, you do illumination in this direction, in this plane, and you measure also in this direction. So you do it in the same plane. So these are all out of plane measurements. So I just show you, there are some, the reconstruction formulas are usually very easy to derive. I mean, you can refer to something which has been done before, but especially essentially the trick is always that you have to integrate out some directions. So you derive equations for an average pressure field, and if you measure vertical lines, you integrate out vertical lines. And if you do this, you reduce the three-dimensional wave equation to a two-dimensional wave equation. And the delta distribution has disappeared, so it's just an inverse problem for the two-dimensional wave equation. And so here these are the measured data. You see now if you put in this parameterization, you can handle more or less arbitrary geometry. But there's this reparameterization going on. The measurement data is parameterized with respect to the angle, but you evaluate the pressure at the tangent point. So if you do this, you can handle arbitrary geometry well, in a very efficient mathematical way. So, well, and then once you have reduced it to a two-dimensional problem, you can refer to all of these reconstruction formulas which are available for reconstructing of averages over spherical means. Well, these are circular means in this case. And so you have exact reconstruction formulas either by series expansions or by reconstruction formulas if you measure at the half space. So the object is, for instance, left to the space. This is actually what they use in this ultrasound, in this combined ultrasound techniques as well. So they use these reconstruction formulas for the half space. You have exact reconstruction formulas if you use a circle and there are also reconstruction formulas if you use ellipses. This is a back projection formula, and this is a series expansion formula. So you have in all these cases very good reconstruction formulas. Just an example, if you use the half-space method, then it's quite easy to explicitly write down the solution. So the initial solution of the two-dimensional wave equation then is essentially Norton's formula, which is from the 80s. So you have here a kernel. This is the boundary where you measure, and the kernel is, well, it's the Fourier transform of this function here, two-dimensional Fourier transform of this function. So just do some inversion with the Fourier transform, and then you can explicitly calculate the initial data from your boundary data which you measure. So all of these reconstruction formulas, they come now in a series. You can do for this measurement geometries if you measure along a plane. For instance, if you here it's then on a circle, and here is a series expansion representation. So again, there are some Bessel functions. I don't know them by heart, but usually you just have a very nice series expansion where you can do an analytical, where you can base actually numerical reconstruction formulas. In this case, you would have to rotate the specimen or the measurement device along the specimen with 360 degrees. But the reconstruction formulas is of the same structure as for the half space. Well, instead of the Fourier transform, you get a series of Bessel functions. And the reconstruction formula is again a convolution, but essentially in terms of polar coordinates. So, and I guess these formulas are very similar to the ones which also have been published in these fundamental papers in the 80s already. Okay. For the ellipses, it looks, I have not here the paper of Agranovsky, but this is a series expansion which you have. So, I mean, essentially it works the same with as with the circle, but you have to use some other special functions. Instead of these Bessel functions, they enter this so-called modified Mathieu equations, but otherwise it's the same. So it's here a series expansion. Here you have modified Mathieu equations. I show you how they look like on the next transparency. And here the Mathieu functions. Before you had just the quotient of the Bessel functions. And here you don't parameterize as before the sphere, but the ellipses. So this is just coordinates on the surface of the ellipses. So these are some reconstruction formulas, and the Mathieu functions are the solutions of this differential equation. So it's well, just the coefficients, the diffusion, not diffusion coefficient, but the coefficient here somehow a little bit nasty. Some of them are with sine functions, and the other ones with sine hyperbolic functions. So I mean, it's just that you see that you can explicitly, also for more complex geometries, give an explicit solution of this photoacoustic imaging problem. Okay, so now if you measure with vertical planes, it's actually mathematically quite nice, because you integrate out planes now in polar coordinates. So you assume that this a cylindrical geometry, all these planes are rotated around the object, and so the illumination is in this direction and the measurements is in these planes, which are outside in this case. If you integrate them out, you get now a one-dimensional wave equation, and you get the initial data for the one-dimensional wave equation. There you have an exact formula, the D'Alembert formula, and once you have this, you do essentially a two-dimensional Radon transform, because you have all planar images all planar averages. So it decomposes in D'Alembert's formula plus the inverse Radon transform. And again, you can do it in arbitrary geometries by this shift transformation, which just arises from the reparameterization. So here you have a very convenient formula. You point detectors. The essential thing is also doing an average integration. You use the parameterization of the sphere where you do the averages. Then you have this delta distribution which you eventually integrate out. So it gives you just point evaluations of this function here. And then you have some, here an explicit formula. And what you see is that it's essentially the integration over spheres with some points which are inside and some radii. And so the reconstruction formula is now with point detectors very simple. So you integrate the measurement data at the boundary. And then you use a reconstruction for the, well, I should not say spherical, but of the circular mean operator, which there are a lot of analytical formulas available how to reconstruct this. So also in this case you get an analytic reconstruction formulas, and horizontal line detectors, again very similar. So you integrate now along these horizontal lines. So this is now in the plane. You get again a two-dimensional wave equation if you integrate along lines in the illumination direction. You get this initial condition. You see this is also an integration over a line. So you can imagine how it works. You solve this PDE, two-dimensional PDE, and then you apply an inverse Radon transform to get the solution. This is now a one-dimensional Radon transform where it's integration along lines, where the other one was integration along planes. So this is here how the reconstruction formulas look like. So there is one thing which appears usually when you go to something two-dimensional, some sort of Abel transform appears, which also appears here. But essentially the first step is just solving the two-dimensional wave equation where you have the integrated data along these lines in the plane, and then to apply a Radon transform. So this is now the conclusion on this sectional imaging. So you have reconstruction formulas for this if you use some focused illumination in the plane. And you can derive reconstruction formulas essentially for arbitrary convex geometries, and especially the integrating detectors have the nicer reconstruction formulas. I should also say that there are some universal back projection algorithms available which should work on every geometry, but I guess the bottom line is they only work in complex geometry, only arbitrary, but in practice they work reasonably well. Okay, so now I would like to also the last few minutes, I would like to concentrate on taking into account some variable sound speed, and I want to reconstruct them with photoacoustic measurements. So it's a little bit more general than before. So instead of assuming a constant sound speed, I always had one before, I assume now that it's variable. And the question is whether we can do it in parallel. So I want to reconstruct F and C in parallel. And of course I have to create more data to do this. And the first attempt which we made is just that we do this sectional imaging. But so far we do it in a very uneconomical way. We create too much data. So we do it really slice by slice, but not the slices also have to be moved. So we rotate also the slices. And this gives us six-dimensional data actually for reconstructing a three-dimensional data. So it's way too much, but we were interested in finding whether with such a method we can find an analytical solution for f and c. Well, and then, of course, the problem with this wave equation can be made also simpler. Well, the measurements could be made simpler, but also one uses typically the Born approximation. Well, not typically, but we tried with the Born approximation first, because then we get still linear problems, and this is the thing, I guess, to tackle to get analytical reconstruction formulas. If we work with nonlinear problems, then we have to do it, probably solve it with numerical methods. But so what we do is we decompose, and I hope I didn't screw up the notation very much. So I want to, the solution of this two-dimensional wave equation with variable sound speed, I express as two functions u and v. And if I neglect second order terms, these functions u and v satisfy the homogeneous wave equation with the initial datum from the photoacoustic problem. And the function v is connected to the function u via this inhomogeneity. And this is just the photoacoustic problem. This is just the Born approximation to split it up into two components. And so that the problem now is I collect data, which is the sum, so averaged u and v. And from the sum of u and v, I want to reconstruct this function f, actually the whole three-dimensional, because I rotate this delta, these slices, and then the function q, from which, well, I can reconstruct at least approximately the function c. If the Born approximation is valid, then this is a good approximation, otherwise it's not. So I can split it up now in two problems, and for all of them, for the single problems, I have the reconstruction formulas. This one is the, well, this is essentially the Norton formulas which I can use for, and this is the sliced imaging techniques which I have shown you before. So this is the idea, to split it up into two linear problems, and then to apply the techniques for each of the, well, let's say ultrasound problem, which is this one, and the photoacoustic problem. So for some reason we went to the Fourier domain. I'm not so sure if this is the most practical way, but well, of course, Andreas has worked with these Fourier methods for a long time, so he knows all this stuff. And so we find it more convenient, but I guess there must be a way also to do it directly on the data. But so we went to the Fourier domain and consider the wave equation in the Fourier domain, which comes up with the Helmholtz equation. So we have two Helmholtz equations, one now for the ultrasound problem, and one now for the photoacoustic problem. And depending on the space dimension, of course, you have different fundamental solutions for these equations. In R3, it's much easier. You have the exponential functions, and otherwise you have the Hankel functions. So it's just that we can express the solutions with these functions. And so you get, after some calculations, and more or less analytical reconstruction formula for the function f. This is now the Fourier transform of the measurement data, which you do, well, which is available in time. And then you have an integral equation where you have the integral over the planes. Here is the function of interest, and here you have, it's unfortunately not, I mean, there's nothing really missing, so it's just one of these fundamental function enters as an additional term. So you have this integral operator, which consists of the product of two of these fundamental solutions. And I guess we have talked about this a little bit, why the the product here appears. I think the product here appears because we have two problems, and we solve first one problem and plug it into the other. So, and every one of these problems is expressed in terms of Bessel function, of these fundamental solutions. So this is, I guess, where the product here appears. Maybe not the physical reason, but it's just that there are two coupled problems, and each of them is expressed via the fundamental solutions. So, and once you accept this, that this comes out, you get, you actually have to do a Fourier transform of your data. Since you collect data, ideally over all planes, which are all averages over planes of the of this function, well, we just have to apply a two-dimensional Radon transform, and then there comes an integral operator which you have to resolve. And well, when you analyze this, you see that it's a Volterra integral operator. The F should be actually, I should put it a little bit more inside, but actually it's the decomposition of the Radon transform and the Volterra operator, which is well posed. So essentially from this data you can reconstruct by Fourier transform, Radon transform, and inversion of a Volterra integral operator, which you apply pointwise, an explicit solution for this problem. So this is written down here. So essentially, it's everything what I stated before is in this formula. So this is the analytical reconstruction formula. But essentially for practical applications, it's not the thing which one really has, because one has to collect too many data currently. And I say especially what I guess the physics people don't want to do is to rotate the specimen and to record slices for different angles. This is technically much more complicated. So, but from a point of dimension analysis, it should be possible to do it also slice by slice. And then it would be a practical way to reconstruct both parameters. But so far we have not achieved this. Okay, thank you very much.
Could we go back 2 slides to your L equation or your L hat equation, whatever you called it?
Well, yeah, I try, yeah.
The previous slide.
Okay. This one?
Yes. Okay. Okay, so you claim that well, I mean, you feel certain that one can show the existence of solutions using whatever integral transform techniques. There's a very interesting equation which is similar to this that Barry Simon has in investigating relationship between spectral functions and the Schrödinger potential in a Schrödinger equation, and he has an equation on this. It's called the A amplitude method, and I'm just looking at the mathematical structure of both your equations, and I wonder whether there actually could be some connection mathematically between the two.
Well, I mean, I cannot answer this, but I have never worked with the Schrödinger equation. That's my problem. But I think, I mean, it doesn't sound so unreasonable. I mean,
is the existence of the solution technically difficult, or is it fairly straightforward?
No, you just have a Volterra equation, and you can decompose it into a compact operator, and you get it's easy. It's very easy. You use a standard textbook result afterwards. So but I mean, it's everything formulated for the Helmholtz equation, and there are these relations, I guess, to this Schrödinger potential. But I have never worked on it, so it would be interesting to look at it from several points of perspective. But maybe we talk offline.
Okay,
Can you say something about the numerical parameters? If you do that numerically, how large is your grid that you're integrating on?
How much? I mean, the biggest data which we get with the resolution is, I guess, 1,000 pixels. I mean, not for the double parameter reconstruction. We've never done this. But the ones where I mean, it's essentially you apply an Abel transform and a Radan transform. So it's not so complicated to do it.
You have, say, kind of Green's functions here, what you're using. So you have to deal with singularities and then.
Well, here we didn't do any reconstructions.
Yeah. Okay. Yeah.
So and probably we have to, but and the other ones, everything is smooth. In the sectional imaging, everything is smooth. So there I don't need these special functions. I mean, when I do this series expansion, I get some problems. You're right, if you are referring to this one. I mean, the Bessel function, when I divide and I get zeros, then I have to do something. But you can work with the L'Hopital's rule. If they get a zero, then you make the L'Hopital, and then you get stable formulas. But you have to check it. But
so I think I see how this goes. It's, of course, always a little miraculous when you have measure the sum of two things and then infer each of them separately, which at first looks like what happens here, but apparently the various ranges of L for various values of X are sufficiently independent that you pin down this common multiplier F as well. Is that how you think about it?
Yeah, I guess this is the right view. I mean, well, maybe not sufficiently independent. I collect so many data that there are enough independent data. That's probably the correct formulation. But there are, I could select definitely some. We have looked a little bit on it, so I could pin it down to less measurements, but then I have to select independent ones. And then it's, I think, more related to yours. Currently we are just collecting data.
What must underlie the success then is that within the sufficiently large volume of data, there are enough independent
data.
ones to
exactly, yeah. And it would be nice if this would be just obtainable by this sliced imaging, because then we could do it directly with the current measurement setups. Well, numerically you can probably do it, but we have not tried it. Then we end up with your problems. Analytically, we don't know so far.
You said that you had the two Green functions, the multiplication of two Green functions. So in fact, in seismic we have the same. When you have a source excited at some point, then so we have a wave coming from that point to a scatter. So this is a phi from the source to the scatter y, and then you have the amplitude y, and then back, and then and then it's recorded to the receiver x.
Yeah. I mean, this could be probably another interpretation or a better interpretation. So this looks like exactly what you said. So it goes from x to y, so it's probably an artificial transmitter or something like this inside the specimen. Mathematically, I guess probably it comes just because we decompose it into two equations, but probably you are absolutely right. I mean, but I've not thought about it. Bill mentioned this to me, so probably.
Let's thank our speaker.